Welcome to Introduction to RLC Circuits Short Course Section 2. In Section 1 we talked about RL and RC circuits powered with DC sources. For the RL circuits we found the current as a function of time, and for the RC circuits we found the charge on the capacitor as a function of time. So in both cases the equations we had to solve were first order differential equations. So the solutions were simply obtained by solving an integral. Today we will cover section 2 of this short course, which involves the RLC circuits powered with a DC source. If you are ready, let's get started. Before we move on to an RLC circuit powered with a DC source, we will first look at an LC circuit, an inductor connected to a capacitor. The reason is that we want to introduce to you the natural frequency concept whenever we have LC circuit elements. So let's start with an LC circuit. The easy one is we just have one L and one C. Okay? So initially the capacitor is charged. Let's say it is charged like this, plus minus. The initial charge on the capacitor is, let's say, Q naught. So at any given time t, there will be some current in the circuit. You may just call it I of t, like that. So with this assumption we say that the current is feeding the positive terminal. So as we know, the current can be written as dq over dt in this case, because this is the positive terminal and the current is feeding the positive terminal. Okay? So now if this is the direction of current and the current is increasing like that, so we will have a potential drop across the inductor as we move like that, and a potential drop across the capacitor like this. So the differential equation we want to solve is minus L di over dt minus Q over C is equal to 0. Potential drop across the inductor, potential drop across the capacitor. So we can simply multiply with a minus sign. These become plus, and I is dq over dt. So this equation gives me L d square q over dt square plus q over c is equal to 0. If I divide both terms with L, I can write this as dq over dt square plus q over lc is equal to 0. So at this point I'm going to define 1 over lc as another constant. The reason will be clear later. Plus, we will call it omega naught square q is equal to 0. So this is the differential equation I want to solve for q. Okay, omega naught square is defined as 1 over LC. So this is how I defined omega naught square here. Okay, so next step is to solve this equation. So this is a second order differential equation with constant coefficients, and this is a linear equation. What does that mean? The meaning of linearity is that if Q1 is a solution and if Q2 is a solution, so these two are two linearly independent solutions. So if Q1 is a solution, Q2 is a solution to this equation, Q1 plus Q2 is also a solution. So this comes from the linearity. So this is a linear second order differential equation with constant coefficients. So the coefficient of the second derivative is a constant, and the coefficient of q here is a constant. And this is a homogeneous equation. In other words, the right hand side of this equation is simply 0. Okay? So in the next step we will look at non-homogeneous differential equations as well. So how do we solve it? From your differential equations class, you know that the solution can take the form. So let's say q of t, we assume that is something like e to the lambda t. So basically what we try to do is we try to solve for lambda. When I take the second derivative of this gives me lambda square e to the lambda t plus omega naught square e to the lambda t. This is q is equal to 0. If you divide both sides with e to the lambda t, this is what you will get. So from here, what you see is lambda could take values plus or minus I omega naught. So lambda is purely imaginary. So I is my imaginary number. As you may remember, I squared is equal to minus 1. Okay. So I have two roots for lambda. So in other words, Q of t can be written as, let's say, a prime e to the I omega naught t plus b times e to the minus I omega naught t. And this is my general solution for this equation. So e to the I omega naught t or e to the minus I omega naught t, they can be written in terms of sine and cosine functions. So let's call it b prime. Q of t can equally be written as a times, let's say, cosine omega naught t plus b sine omega naught t. Either one of these solutions can be used. So how can we determine A and B here? Well, we use the initial conditions. So initially, we know that the charge on the capacitor is Q naught. So we know that Q, when t is equal to 0, is equal to Q naught. But what is the current in the circuit? As we all know, due to the presence of inductor, the current cannot increase rapidly, right? So initially, we can safely say that the current in the circuit is equal to 0. So there is no current initially. Okay, using these two initial conditions, we can actually solve for A and B. So let's find I of t first. The current in the circuit is given as dq over dt, right? So the derivative of this, so these are my initial conditions. Let's not get confused here. So this gives me minus a omega naught sine omega naught t plus b omega naught cosine omega naught t. And this is my current. So the current when t is equal to 0 is equal to 0. So I will use that initial condition first. So 0 is equal to, when I put 0 here, this term is 0. When I put 0 here, cosine 0 is 1. So this gives me b times omega naught is 0. So this actually tells me that b must be equal to 0. So this is how we solve for b. Okay, so here b is equal to 0. We can use now the first initial condition, Q naught, right? So using this, we already know that Q of t is simply equal to a cosine omega naught t, because we inserted this over here. Okay, so Q naught, so when t is equal to 0, this is equal to a. Okay, very good. So let's write down the solution. So Q of t is simply equal to Q naught cosine omega naught t. And I of t is simply equal to minus omega naught Q naught sine omega naught t. And these are the time-dependent quantities for this LC circuit. So what do we see here is they actually oscillate, right, with this omega naught frequency. Sorry, by the way, this is omega naught t here. So these two quantities actually oscillate with the frequency omega naught. And one is a cosine function, the other one is a sine function. Okay? Those don't make sense. So omega naught here is defined as the natural frequency of the LC circuit. It is really crucial to know what this omega naught is and how we define it. Omega naught is equal to 1 over square root of LC, because we will keep seeing this omega naught over and over when we are dealing with RLC circuits with DC sources or RLC circuits powered with AC sources. So we will keep seeing this omega naught a lot in the future topics. So that's why it was crucial to study this LC circuit before we move on. So if we plot Q and I here, so Q as a function of time t, so it's like a cosine function, right? So the charge on the capacitor decreases and then increases again. So this is like an oscillation, right? So the value here is Q naught. So when time t is equal to 0, the capacitor is initially fully charged, Q naught, and its value changes between Q naught and minus Q naught, right? As time goes by, this is minus Q naught. So what happens to the current in the circuit? So if you want to plot current as a function of time t, hence they have the same frequency, right? Okay. This is good to see. So let's suppose this point is here. Let's look at this point here. Let's say this is here. And this is one cycle, right? So now, current is initially in the opposite direction, right? There is a minus here, and it's like a sine function. So it reaches a maximum here. So when the charge on the capacitor is 0, the current in the circuit has a maximum value in the opposite direction. And then when the charge on the capacitor is max, right, the current in the circuit would be 0. So when the charge on the capacitor is 0, the current in the circuit would be max, and then it will again be 0. And this is one full cycle for the current. So initially it is 0, and at some time t, like quarter of the period, the current would be minus omega naught Q naught. And this value here would be omega naught Q naught. Okay? So physically, what does that mean? Initially, the capacitor is fully charged, okay? And then the current in the circuit is 0. So this was the direction of the current I chose initially. So if the capacitor is charged like that, the initial current would be running in the opposite direction, right? So that's why it's increasing in the negative. Okay? And it starts to increase. It starts to increase with time. The magnitude of the current increases. So when the charge on the capacitor is 0, the current becomes max. Okay? And then it's now feeding the opposite terminal here. So that's why the value for Q becomes negative, because we are now feeding the other terminal here, which we assume to be negative terminal initially. So when this terminal is fully charged, we are here, okay? So the current in the circuit becomes 0, but now the capacitor starts to discharge in the opposite direction, that direction, which I assume to be my positive direction for the current. That's why the current becomes positive here. And the cycle repeats itself indefinitely. So this is a typical oscillation we see in LC circuits when there is no any resistor. So in the next few steps, so today we will also discuss RLC circuits where you will see the effect of the resistor. So whenever we have resistance, this oscillation cannot take forever, okay? There is always a damping. So in reality, we cannot create LC circuits like that, right? Even the simple wire has some sort of a resistance. So there is no way actually to create this idealistic situation like an LC circuit, which oscillates forever, right? So I think it's all clear. Now we will move on to the next topic where we will have an LC circuit powered with a DC source. Now we will look at an LC circuit powered with a DC source. Based on this setup, we have a positive terminal of the battery here and a negative terminal here. So at any given time t, I again assume the current is running in this direction, feeding the positive terminal of the capacitor, just like that. So let's write down the equation for this circuit. I will have a potential drop across the inductor as the current increases in this direction. So you'll have minus L di over dt. minus Q over C, as usual, the potential drop across the capacitor, and then we will have a potential increase here, V naught. V naught is a constant since it's a DC source, right? So if I multiply everything with a minus sign, this becomes plus, this becomes minus, but I can put V naught on the other side. So in the end, I'll have equal to V naught. So this is similar to the equation I solved before, except the fact that I have a positive term here. So as usual, we know that the current is feeding the positive terminal of the capacitor, so I can simply call I as dq over dt. So this becomes L d square q over dt square plus q over c, which is equal to V naught. At this point, I can divide everything with L, so this becomes LC, this is L, but I defined a quantity called natural frequency, right, omega naught, which is 1 over square root of LC. So this term simply becomes omega naught square times Q. So this is good. So this is similar to the equation I solved before, but I have a constant term here. So a typical solution to this type of differential equations is given as this. So I will have a complementary solution plus a particular solution. So Q, the solution to this equation is composed of two parts. One is the complementary solution, the other one is the particular. The complementary solution is the solution to the homogeneous differential equation. In other words, d square Q complementary, dt square plus omega naught square, Q complementary is simply equal to 0. So Q sub C is the solution to this equation, which we already solved in the last board. So we can simply write Q sub C as A cosine omega naught t plus B sine omega naught t. So this is the solution for the complementary part. Okay, so we need to find QP, the particular solution. So in order to find it, we looked at the non-homogeneous part, in other words, the right-hand side of this equation, which is a constant. So since it's a constant, what you assume is the Q particular would be another constant. So when you insert this constant in the original differential equation, the second derivative or the first derivative is simply 0, right? It's a constant. So this equation gives us omega naught square times k is equal to V naught over L. In other words, k is equal to V naught over L times omega naught square, but k is equal to, so omega naught square is 1 over LC, so this is simply c times V naught. So we solved for this constant, and it's actually the solution, particular solution for this differential equation. So we can simply write that QP is equal to C times V naught. Okay, very good. So now the full solution would be equal to A times cosine omega naught t plus B sine omega naught t plus C times V naught. So using this, we can actually find the current as well. So minus A omega naught sine omega naught t plus B omega naught cosine omega naught t. So how do we find A and B here? Well, again, the initial conditions. So let's suppose initially the capacitor is uncharged. So we can say initially Q0 is equal to 0 and I0 is equal to 0 because there is the inductor, right? So these are my initial conditions. Let's say initial conditions. Okay. So with these initial conditions, it is different than before, right? Because in the previous example, in the previous LC circuit, we actually put some charge on the capacitor initially, right? So Q0 was Q naught. But here I'm choosing a different initial condition. It's easy to use the second one first. So this is 0. This means that it implies that 0 is equal to, so sine 0 is 0, cosine 0 is 1, so this is b times omega naught. So this implies that b is equal to 0. Okay, so if b is equal to 0, this is going to be 0 here. Let's look at q. q0 is also equal to 0. So this implies that 0 is equal to, cosine 0 is 1, so b is already 0, plus c times v naught. So this implies that a must be equal to minus c v naught. Very good. So the solution for q is equal to c times v naught parentheses 1 minus cosine omega naught t. And the current in the circuit is equal to c v naught omega naught sine omega naught t. So these are the solutions. So as you see, we again have oscillation. So q and I, they both oscillate. However, for q, I can actually reach values which is twice as the CV naught. So the potential drop across the capacitor can be 2 times V naught, right? Because cosine omega t can take a value of minus 1. So if it's minus 1, so let's look at Q max. This is something really interesting. So Q max is equal to 2 times C times V naught. This is interesting. So the potential drop across the capacitor can take a maximum value of 2 times V naught. How is that possible? So this provides V naught and this becomes 2 V naught. So at that instant, the potential drop across the inductor is simply minus V naught. Okay? We can also show that. So when we look at the charge on the capacitor, what we see is, well, cosine function takes values between 1 and minus 1, right? The minimum value for Q is simply 0. Q will only take values which are positive. So initially, we are here. So the value of Q increases and then decreases and then decreases and then increases again, right? So this oscillates like that. This is quite interesting. And the maximum value here, Q max, is simply equal to 2 times C times V naught. This is Q as a function of time t. So the oscillation takes place about this CV naught. What this means is that by introducing a DC source like that, we have shifted the equilibrium point of the oscillation, right? So it's kind of a bias. If you look at the current versus time graph, so let's plot I versus time here. So this is simply a sine function. So it increases like this. So let's suppose this is my... So it increases first, and then decays, and then increases again. That in the negative direction. So this is how the current in this circuit changes with time. Now we will analyze an RLC circuit powered with a DC source. So at any given time t, I assume that the current is running in this direction and it's increasing. So the potential drop across the resistor, now we have a resistor, be careful, we have minus IR, then I have a potential drop across the inductor, minus L di over dt, and then I have minus Q over C, the potential drop across the capacitor. So now I'm moving in this direction, so my potential increases by an amount of V naught. So this should be equal to 0 because I complete the loop. So as before, I'm multiplying this equation with minus 1. So this becomes plus, and this becomes minus, and I can put V naught on the other side. So this is simply equal to V naught. As I know, I is related to the charge on this capacitor through this relation. I is equal to dq over dt. and I have already defined omega naught as 1 over square root of LC. It was the natural frequency of an LC circuit. Okay, so if I divide everything with L here and use these relations, what I get is d square q over dt square. This is this term here, and plus I have r over L dq over dt. This is this term here, and then plus I have omega naught square q, it's this term, is equal to v naught over L. Okay, so at this point I will define another quantity which I will call it alpha. So alpha is defined as r over L. So I call this damping factor. This is how I define it. So the damping is, of course, due to the resistance here, right? So that's why it's equal to r over L. Okay, this is again a second order differential equation with constant coefficients, and it's also linear, and it has a non-homogeneous part here. So this side is not 0, right? If it was 0, this would be a homogeneous, right, differential equation. So again, as usual, this will have, the solution to this will have two parts. So Q of t can be written as Q complementary, which is a function of time t, plus Q particular times t. Okay, our goal is now to find the complementary solution and then the particular solution and simply add them up. So for the complementary solution, we assume that, let's assume Q complementary t is equal to e to the lambda t. Similar to what we did before. So as you may remember, the complementary solution is the solution to the homogeneous part of this equation. So in other words, dq dt square, d square qc over dt square plus alpha dqc over dt plus omega naught square qc is equal to 0. So the complementary solution is the solution to this equation. Okay, so if I take the second derivative of that, I'll get lambda square, right? So lambda square plus I have alpha times the first derivative is just lambda e to the lambda t, right? So this is lambda plus omega naught square. So everything multiplied with e to the lambda t, and this should be equal to 0. Okay? So if this is the case, what I can say is e to the lambda t cannot be 0, so I will have a quadratic for lambda, right? Okay. So now the solutions to lambda, so I will call it lambda 1, 2, will be equal to minus alpha plus minus square root of alpha square minus 4 omega naught square, right, over 2. In other words, so lambda 1 or 1 and t can be written as minus alpha over 2 plus minus square root of, say, alpha square over 4 minus omega naught square. As you see here at this point, if alpha is 0, in other words, when r is 0, we have the usual LC circuit, right? When alpha is equal to 0, I will have square root of minus omega naught square, which would give me plus minus here I omega naught, right? And this is what I got before. But in this case, we also have the resistance R. That's why I have this damping factor in the solution. If I look at this lambda term here, now I'll have actually 3 different cases. So case 1, so this is my lambda 1 and 2. So I'll have 3 cases. Let's suppose case 1. What can I have for case 1? So I can have alpha over 2 can be larger than omega naught, right? So the term in the square root can be a positive term. In other words, I'll have real solutions for lambda, right? So if this is the case, the system is called as overdamped. So the damping is strong, right? Okay. So in this case, lambda 1 and lambda 2, they'll be both less than 0, right? Because this term here in the square root, the magnitude of this term is always less than alpha over 2. So lambda 1 and lambda 2, they are both less than 0. So if I look at the complementary solution, okay, the complementary solution in this case would be given as A e to the lambda 1 t plus B e to the lambda 2 t. So this will be the solution for the complementary part. Okay, so case 2, so in case 2, alpha over 2 can be equal to omega naught. Okay, so this would be simply 0, right? So the solution for the complementary solution will take the form e to the A times e to the minus alpha over 2t, right? I have minus alpha over 2 here, e to the minus alpha over 2t plus b times, so here I cannot have the same e to the minus alpha over 2t, right? Because this would be not linearly independent. So if you go back to your lecture notes in your differential equations class, the linearly independent solution in this case is given as t times e to the minus alpha over 2t. So we simply multiply this solution with t, and this gives us the second linearly independent solution for this case. So this case is also called critically damped. So critically damped. Physically, it's really hard to see any circuit which is critically damped because it requires a precise fine-tuning here of these parameters, right? So alpha over 2 should exactly match omega naught. Okay? So what is case 3? So case 3, in case 3, we may have alpha over 2 less than omega naught. And this is called underdamped. So in an underdamped system, the solution for the complementary part is simply given as e to the minus alpha over 2t, parentheses. So this term would be simply imaginary, right? Because omega naught is larger than alpha over 2 here. So what we can say is we will have an oscillation here. A times cosine omega 1t plus b sine omega 1t. So what is omega 1? Omega 1 is defined as square root of omega naught square minus alpha square over 4. For case number 3, where this circuit is underdamped, in other words, the damping factor is not as strong, we again see some oscillations like we saw for the RLC circuit. However, the frequency here is a little bit different than omega naught here due to this alpha square over 4 here. So there is an oscillation. However, this oscillation decays due to this exponential decay term here. So if we wait long enough, this solution tends to 0 as well. So now we have these 3 cases for the solution for the complementary part. So we need to find a particular solution now. Since the right hand side is just a constant, we will assume that Q particular is a constant. So if we insert this in this equation, we again have omega naught square times K is equal to V naught over L, and as before, K turns out to be C times V naught. The particular solution here is simply equal to C times V naught. Okay, so regardless of the type of damping we may have in this circuit, particular solution is always the same, which is C times V naught. One thing that we need to see here is that whichever damping we may have, the complementary solution always tends to 0 as time t goes to infinity. So if we wait long enough time, we do not see any of these solutions in our system. So if we wait long enough, we do not see any of these solutions in our general solution. In short, what we can say is limit when t goes to infinity, okay, QCT, complementary solution, tends to 0. So it's easy to see that this holds true for any of these three cases here. So if we wait long enough, limit when t goes to infinity, okay, Q of t is simply equal to C times V naught. So in other words, if we wait long enough, the potential drop across the capacitor would be simply equal to V naught here, and the current in the circuit should tend to 0, right? So this is also another observation here. So limit when t goes to infinity, the current in the circuit must be equal to 0. At this point, some may ask how we can find the A and B values here. It is the standard procedure. You look at the initial conditions. So whatever the initial conditions are, you just insert them and then you find A and B. We will now solve an example problem to complete this section. We would like to complete this section by solving this example. So in this problem, what it says is for the given underdamped RLC circuit, we would like to find the charge on the capacitor as a function of time, such that initially when t is equal to 0, charge on the capacitor is 0 and the current in the circuit is equal to 0. So in the last board, we talked about the solution Q of t. So Q of t is actually equal to the complementary solution plus the particular solution. So the particular solution in any kind of damping was the same. So C times V naught. We already solved that. However, the complementary solution takes different forms depending on what kind of a damping is in this circuit. Since this is an underdamped system, Q of C is simply equal to e to the minus alpha over 2t times a times cosine omega 1t plus b sine omega 1t. Okay, so alpha is defined as R over L. This is the damping factor, and omega 1 was square root of omega naught square minus alpha square over 4. Okay, this is good. So now starting from here, what we can write is Q of t is equal to e to the minus alpha over 2t times a times cosine omega 1t plus b sine omega 1t plus c times v naught. And this is our particular solution. So using this, we can actually find the current as a function of time. The derivative of this, the first, is minus alpha over 2 e to the minus alpha over 2t times the term in the square brackets plus the derivative of the second term times the first, which is e to the minus alpha over 2t times minus a omega 1 sine omega 1t plus b omega 1 cosine omega 1t. So at this point, we will use the initial conditions. Q0 is equal to 0, I0 is equal to 0. So let's start with I0 is equal to 0. So this actually tells us that 0 is equal to minus alpha over 2 times this term. Cosine 0 is 1, sine 0 is 0, so this is simply equal to A, plus, when t is equal to 0, this is 1, this term is 0, plus B times omega 1. Okay, so from here, what we can say is B is equal to alpha over 2A over omega 1. So that's good. So this is how we can write B in terms of A. Okay, let's look at the other initial condition. Q0 is equal to 0. So this actually gives us that. So this is 1, cosine is 1, sine is 0. So this is nothing but 0 is equal to A plus C V naught. So this simply tells us that A is equal to minus C V naught. So B is simply equal to minus alpha over 2 omega 1 C times V naught. So now we can write Q as a function of time t. So we have one CV naught here, we also have CV naughts here. So C times V naught, parentheses, 1 minus, well, these terms also have this decaying factor, e to the minus alpha over 2t, parentheses, A is just 1 cosine omega 1t. So I put the minus out here, then I'll have plus alpha over 2 omega 1 sine omega 1t. We close this parenthesis and this one too. So this is our answer. So this example actually shows how to apply the initial conditions to determine these coefficients A and B. Similarly, for the overdamped or critically damped systems, we can actually follow a similar procedure to find the coefficients A and B for those systems. This completes the section 2 of Introduction to RLC Circuits Short Course. I hope you enjoyed it. If you have any questions, please write them in the comments. In the next section, we will look at AC-powered RLC circuits. I look forward to seeing you in the next section.